in our session. I'm sorry, I have to leak my papers. Is I don't know, Andreea, Badicu, Hugo, Daniel.
It's me,
yeah,
Hugo.
That's you. Unfortunately, I have nothing about you.
No worries.
Because I had the introduction talk only just for Hugo Macedo. So please, yeah, that's you. Yeah. So you are a permanent research staff at the Cyber Physical System Group in the Aarhus University, and is a co-PI. PI, what's mean PI? That
principal investigator, or we coordinate the HUBCAP project.
So not private instigator, but
no.
instigator of the HUBCAP project. So please start the presentation now. Thank you. The floor is yours.
Let me try to share the video that we have. So this was prepared by me and Andreea.
Welcome everybody. My name is Hugo. I'm from Aarhus University.
My name is Andreea Badicu from Bear Consulting International.
And we're here to present a paper that we submitted to the SESDE workshop. The paper is about deploying the smart energy tool for investment simulation inside the HUBCAP sandbox. So a tool used for model-based design of energy being deployed in the HUBCAP sandbox, a platform that is new. And
excuse me, we lost the voice. Could you please unmute yourself?
So you're saying that if I'm sharing, it mutes automatically?
This is happening constantly. In other words, you get about 30 seconds worth of voice, and then we have to use our plan B for the to present it on his screen. Just FYI.
Yeah. So Mohammed, do you want to share my video then, please?
Sure.
Number 29.
Sure. Okay.
Thank you very much.
welcome everybody. My name is Hugo. I'm from Aarhus University.
And my name is Andreea Badicu from Bear Consulting International.
And we're here together to present a paper that we submitted to the SESDE workshop. The paper is about deploying the smart energy tool for investment simulation inside the HUBCAP sandbox. So a tool used for model-based design of energy being deployed in the HUBCAP sandbox, a platform that is new. And let's talk about it. So first things first, what is HUBCAP? HUBCAP is an innovation action. It's a project co-financed by the European Commission. And basically, it has a goal of providing a one-stop shop for European SMEs wanting to adopt model-based design in the development of their cyber physical systems. So we do that by providing a platform, hosting model-based design tools and models that are ready to use for by users. And at the same time, we also host an open calls program where SMEs can win up to €1,000 to deploy their model-based design tools or models as assets in our platform to be used by other people. And we will also this fall open a call to experiment where two SMEs can jointly apply to our call to do an exchange of model-based design assets and receive up to €75,000. But back to our contribution. Basically, our tool is, or the tool that we are featuring today, is available in the HUBCAP collaboration platform, meaning that when a user logs in, if he's looking for an energy simulation tool, he can browse our catalog of tools. he could find this one in specific. And the idea is that if the description looks fine and this would be a match, they could use the web browser to both read about it, know it a bit better, but also to push button and start to get an environment, a HUBCAP sandbox, where the tool is ready to use and where they can just have a common development on top of if wanted. So basically, the HUBCAP sandbox is just part of a web app where we feature a shopping cart where a user can just add this tool, for instance, and some other tools that he wants to run in the shopping cart, pushes the button, and eventually he receives a web page where the tool is ready to interact with. We have a focus on collaboration. So basically, the middleware provides you access to a virtual operating system that provides all the dependencies necessary to run a certain tool. But you can also invite other guests, and these guests can interact with that operating system at the same time as you're operating. So in some sense, like kind of it allows like kind of collaborations. That allows you to like kind of co-develop a model with some user, highlight what is the features of it, and indeed like kind of foster this collaboration environment. So behind the under the hood or behind the scenes, the HUBCAP sandboxes are hosted in an infrastructure that you would find in any cloud provider. So basically, the broker, like kind of whenever you add tools and models to the sandbox, just prepares all the operating systems, virtual machines that you may need. If you need several of those, you may need them connected via VLAN. We have a network file system that will provide models that are shared among the different machines. And basically, like kind of everything is run in the cloud, and the user just needs to push button and interact with the tools and models. So the tool that we are talking about today is the Smart Energy tool, and Andreea will now take the floor to talk about it.
Thank you, Hugo. So the Smart Energy tool is built upon a platform developed by BEA for real-time energy monitoring, for simulation of energy production potential and assessment of the economic viability of various investments in the energy field. The tool uses historical data to assess the consumption trends specific to an end user and weather data to estimate energy savings. Different scenarios can be simulated to determine which investment is most appropriate for financing, thus reducing investment risks and promoting better management decisions for new project implementations. Next slide, please. For the integration of the tool within the HUBCAP ecosystem, we had to go through two stages: the virtualization process and the consolidation of the tool within the HUBCAP sandbox. The virtual setup was made on a virtual machine, and the parameters were chosen specifically to meet the needed requirements. We used 50 gigabytes of memory, 4 gigabytes of RAM, and Ubuntu OS. No adaptations had to be made for the execution of the tool. Its performance was tested with good results. We used Apache Bench for backend performance and Google PageSpeed Insights for front-end performance. In order to execute the Smart Energy tool platform on the HUBCAP sandbox, we created a Docker version of the platform. First, we had to install a Docker application within the sandbox, and after that, we deployed the Docker version of the Smart Energy application. Next slide, please. Yeah, so to sum up the process, the application was tested with good results, and the performance of the tool was not influenced by the sandbox environment, and no limitations nor restrictions had to be made. The process was very straightforward. We created a new sandbox with Ubuntu OS. The Smart Energy tool was easily installed, as it runs within inside Docker containers. And the Sandbox created also contains a version of Mozilla Firefox, which is the only web application necessary for running the application. On the next slide, you can see a demo of the tool deployed in the HUBCAP ecosystem. Here you can see the platform authentication or account creation, where the user can log in within the smart energy platform. Two different scenarios can be created describing the investment opportunity. Specific rules can be defined for each scenario, and they can also be compared. The user can visualize data by selecting the sensor and the time frame for the representation. The evolution of energy consumption can be plotted hourly or daily, and the data can be visualized in a tabular form or as graphs, columns, and pie charts. So back to you, Hugo, for summing up.
Great, thank you, Andreea. So indeed, to sum up our presentation today, we have this one-stop shop for model-based design of cyber-physical systems, the HUBCAP project. We use cloud to lower the entry barriers for people trying to experiment or adopt tools and models in their design. So one of the tools that was just featured and described by Andreea is the Smart Energy Investment Simulation tool. It's in our catalog, ready to use. And please check our open calls that will be open this fall. Other than that, we thank you for your attention and hope that you read our paper, and any questions we will be glad to answer. Thank you all.
Thank you.
Thank you for the presentation. It was very interesting. I wonder who is this tool is mentioned. Okay, we have a question here. John, please start it. John Richardson, please.
Yeah, there's the Society for Computer Simulation International has a conference. It's a nuclear and power plant and simulation conference, SESDE.org, and just in case you're looking for other places to submit papers, just thought I'd tell you about that. Okay.
Oh, thanks. Can you drop your email in the chat, or so I can get the, or at least drop the conference in the chat? I would like to be in touch and check the conference.
Sure. And there's another paper on nuclear or something or other. I forget what, but those people may be interested. I'll put my email in the chat. Thank you very much.
Thank you very much, John.
Okay, thank you. Any other questions? Okay, I have a question practically, so that's it's not very clear for me whether this tool can be used by ordinary people as well, if they want to organize something at home with their own energy consumption.
Well, I'm not kind of fully into the details of the tool. I know that they should be it should be used by experts in energy simulation, but the company itself may develop a version for user consumers, right? As unfortunately, I think Andreea is not here. Otherwise,
I am here. You're right.
Is here.
You're
oh,
right.
Josh, you're the one to answer this. Sorry.
Yes, you're right. So basically, we have a version that is TRL6. So it was somewhere tested in the lab, but the purpose is for experts to use the tool in the energy sector. So
okay, I thought so. Thank you very much. Any other questions? Abderrazzak, please, your question. Abderrazzak, I don't sure in your name. I'm sorry. you are raised your hand, so if you can put your question now.
Yes, thank you so much, Professor Sebastian and presenters. This is quite a great and interesting actually topic. My little question is about actually the application of this tool. Like, can we use it to monitor, for example, energy from solar panels?
Yes, yes, it's based on real data that comes from the sensors, and based on the data that is monitored, we can do an estimation of the profit we get.
Okay, thank you.
Okay, no more questions then. Thank you very much for the author. It's a very interesting paper. I would like also contact you and find out some details about it. But the time is going fast and we have to move to the next paper. Presentation at my paper is a new one, P84. It was originally meant for tomorrow, but now it's Abderrazzak Boukili has the mathematical and numerical investigation of diffusion in silicon-based solar systems. The program has changed, you know.
All right.
Abderrazzak,
Yes, thank
present. You. Yeah, please start your presentation.
Yes, Sam. All right, so I'm going to share my screen and also the sound as you suggested. And I'm going to play the video for you. It is 16 minutes. I hope you are going to enjoy it. All right.
60 minutes. It is not okay. Let's start it because we have
like that. You have no time for questions.
No time for questions. It's definitely.
Hi everybody. I hope you are all doing well and safe today. My presentation is about modeling and simulation of texturing effects on ion diffusion in textured solar cells. So here are the main objectives of this presentation. So first I'm going to define the problem to solve. And my work is about the optimization, basically, of the efficiency of solar cells. After that, I'm going to share with you the new models that they have developed to help solve the problem. I will present you the numerical results, discuss some of the findings, and conclude the presentation. There are two types of solar cells. We have solar cells that have flat top surface and solar cells that have textured solar cells, textured surfaces. So myself, I am working on the optimization of the electrical and optical performance of textured solar cells. To fabricate either flat or textured solar cells, there are some main steps that we have to use. So one of the main steps that we need to fabricate a solar cell are ion implantation, ion diffusion, oxidation, and electroplating. So in this presentation, I'm going to show you my contribution into developing some enhanced ion implantation models and ion diffusion models that actually will include the texturing effects on the performance of solar cells. And what I mean here by performance, actually, I mean the efficiency of solar cells. We should know that given the status and the progress that has been made in the fabrication and the operation of solar cells, the current solar cells have only an efficiency of the order of 15–16%. That means the modern solar cells can convert only 16% of the sunlight into electrical power. So there are a lot of losses, and there's a lot of room for research and development and innovation and so on. So in this work, I am concentrating on optimizing basically the ion implantation and diffusion processes that are needed in the fabrication of solar cells, either textured or not textured. I am working on textured solar cells. For example, one of the issues that we have in the implantation of textured solar cells is to find the right angle of implantation. What is this angle represents? This angle represents actually the angle between the ion beam coming from the implanter machine and the three surfaces of the pyramids that are making the texturing. Right. So my goal, my objective in this work is to help at least get some ideas about the size, about the right size of this angle, because the implantation of the implantation of textured solar cells depend on this angle. The same thing, the diffusion also of the dopant will depend on this angle, and of course the efficiency of solar cell will depend also on this angle, and this angle is also depending on the geometry of the texturing. So different geometries will introduce different angles. Okay, so let's learn now how to introduce. Before actually I talk about how to find the relation between this angle and the equations of the ion implantation and ion diffusion, I can share with you some of the different types of texturing. As you can see here, we have different types of texturing, and they have different geometries, which will affect significantly the choice of this angle. All right. To find the relation between this angle that affects actually the implantation process, what I did myself is to represent the incident ions or the beam of incident ions by a vector, and they represent also the set of ions that are going to penetrate the solar cell with another vector W. And the idea is just to find is first to find the angle between this vector and the normal to the surface of a pyramid, and from that relation I'm going to find how the dose phi, which represents the number of incident ions, will depend on this angle. All right. So I will myself I will define this angle theta as the angle between the vector V, which represents the set of incident ions, and the normal to one of the pyramids surface. Using some very simple vector analysis, I found actually that the dose that I call here the effective dose, which represents the number of ions that will penetrate the solar cell, because the number of ions that are coming from the implanter machine, not all of them will penetrate the solar cell. Some will be reflected by the pyramids, and that's another problem. But that's how it is, right? Because these pyramids, they have an advantage basically to absorb more light, but they are causing some other issues and some other problems to implantation, to diffusion, and so many other fabrication steps. So using some simple vector analysis, I was able to find a relationship between this implantation angle theta and the different doses that we have in the implantation process. Done. Now I will show you the relation that exists between this angle and the doping concentration. For example, in the classical models where we use Gauss method or Gauss model to represent the doping distribution, here is the expression that we have. C here represents the density of the doping of the dopant. Phi represents basically the number that we call the dose, represents the number of incident ions. And here we are using basically an exponential based model. And this is a classical Gauss model. In the classical Gauss model, as we can see here, actually there is no theta. Right? I put here a theta, but there is no theta here. There's only phi. In the new model that I have developed myself, I did replace phi by phi cosine theta. And this is actually the innovation in this model. And thanks to this relation, I'm able to control and investigate the effect of this angle on the doping concentration and also on the diffusion concentration, because diffusion depends on the dopant. Now let me show you the model that I use for diffusion. This model is based on pair diffusion theory. It involves, as you can see here, 6 equations. The first equation is Poisson equation. Then you have the different equations for the diffusion of different species. In the diffusion process, we have 5 species. We have the dopant that are unpaired, which I represent here by A. Then you have the dopant that are paired, that means that are bind to some defects, which are interstitials and vacancies. Then you have also some other species that represents the free interstitials and free vacancies. So these are the 5, I can say the 6 equations that represent the diffusion equations. And where is the relation between these equations and theta? It will come up actually from the flux of different species, as we can see here, which depends from the flux and also from Poisson equation. If I look at the Poisson equation, I have a function called C sub net, which represents the net doping. This function here depends on the doping of different dopants, which are represented by the subscript here I. Right? I can represent, for example, boron. It can represent phosphorus. It can represent all kind of dopants that you are going to implant. All right. Now this concentration C sub I will depend on theta, and this is the innovation. In the classical model, this function C sub I depends only on phi, does not depend on theta. So that's all. This is the innovation in the diffusion model. So let's move on to numerical results. I have fabricated a sample here, a sample of a 2D solar cell, where the dose is 10 to 15, the energy of implantation is 10 kilo electrovolt, the depth is 0.4, the length 0.3, temperature of diffusion is 1000, the time 20 minutes, and then I'm using here the boron as the dopant because I'm working on N-type solar cells. All right, so let's check what happened and find out what we got. So the first pictures here represent. First one represent the diffusion profile of boron on a flat solar cell, and this one here represents the boron diffusion on textured solar cell where the angle is 36, where the angle of implantation is 36. All right. What are the findings? As I can see right away here, if I compare the diffusion of boron or the diffusion profile of boron on textured solar cell at the bottom and on flat solar cell, I can see that on textured solar cell, I got a smaller maximum value of the concentration and also a lower depth. The depth is about 0.07 microns, which is smaller than the depth we have on flat solar cells. Of course, there are so many other outputs from these simulations, but here I'm concentrating only on looking at the depth and the maximum values. if I move on and compare what happened to the diffusion profile with respect to different angles, I can see here that the same findings. If I look at the profile for 32 degree and the profile for 64, I can see as well that as we increase the angle of implementation from 32 to 64, we get smaller maximum values of the concentration, and also we get a lower depth. So this is a new finding coming from the effect of the angle. Now, to validate these results, I have actually double-checked what I got to make sure everything is fine. I compared what I got, the profile I got with the experiment. And I can see that qualitatively, the behavior is very similar, and the profile aligns very well, excellently well with the experiment. Right? For example, if I go look at the middle here, where I have where the dose is about 10 to 15, you can see that the profile is very similar to the profile I got. Then from the qualitative point of view, the model is right and the findings are right. But from the quantitative point of view, I cannot compare because there are so many inputs that are different. All right, that's all about this presentation. The new findings and conclusion. What I can say is that when I use or the implementation and diffusion on textured solar cells will involve some new challenges. For example, the textured angles lower the ion implantation doses. The textured angles lower the depth of diffusion profiles. And from the experiments, from numerical simulation results, what I recommend myself is implantation angles around 30 degree. Because for 30 degree, I got results that are close to experiment. And also the profiles look accurate and look reasonable. Future work in the next basically activity, I will concentrate on the effect of dual texturing, because here I worked only on a top texturing, but we may have solar cells that have texturing on the top and on the bottom. So I hope you have enjoyed this presentation. Thank you all. If you have questions, please go ahead.
Sorry, we have no time for questions. We got very behind the schedule already. It was very interesting, and it's really a pity that it is not a personal meeting where you can put questions even on the coffee break. But we have to move to the next presenter now. Fortunately, the paper P44, the video has been transferred, and probably we can now just get to this presentation. This is the new intelligence power adjustment of the wind energy conversion system excluded with virtual flux based direct power control using new fuzzy PI controller. Hamed Khaled Eddine, please introduce yourself, and if you can, you start it.
Yes, sir. Good morning, everyone.
Excellent.
Presentation. I am very happy and lucky to participate in this perfect conference. Today, I am presenting new intelligence power adjustment of the wind energy conversion system extended virtual flux fuzzy direct power control using new fuzzy PE controller. My co-author is Hugo and Abderrazzak. First, I start with presentation plan, which contains problem and objective, exist solution, our solution, results and simulations, comparison to the state of the art, and conclusion. Problem. More researchers focus on replacing the pure integrator by using indirect field-oriented control (IFOC), consists in adjusting the flux by components of the current and the torque by the other components. For this purpose, it is necessary to choose the Q reference from rotating synchronously with the rotor flux space vector in order to achieve decoupling control between the flux and the procedure torque. This technique allows to obtain a dynamical model similar to the DC machine. However, the problem of flux, control structure, system stability, active power, PWM, amplitude, and phase deviation is caused. Objective: this paper proposes a new method for virtual flow estimation that is inherently capable of handling these problems. As a result, a stable and smooth virtual flow estimate and DC link voltage and sector detection with precision and more system stability. Active power. The suggested method is based on utilizing new phase controller. Exit solution. This design uses a more robust structure known as the indirect field-oriented control. In this drive system, the indirect flux-oriented control of the FIG using the phase PE controller. The diagram contains the calculation blocks for desired rotor currents and voltage, the part transformation block, a PWM inverter on the rotor side, and the model of the FIG in the park from Badicu. Modeling indirect field-oriented control. So we have the modeling of the turbine, the modeling of the multiplier, and the generator using in this SESDE system is a W-feed induction generator. So we have the FIG modeling. We set flux ds equal flux s and flux qs equal 0. So the modeling of this system will be like this. And this figure illustrates software field-oriented control technique. Our solution: structure virtual flow bus direct power control using new phase PE controller. Modeling new virtual flow flux bus direct power control using phase PE controller. The active and reactive power are controlled by two regulators, hysteresis, the measured value of the powers being estimated from a relationship. 2-3 level hysteresis regulator are used to generate the respective active and reactive power. Sets SP and SQ as figure 1. And we have a switching table, and figure 2 illustrates voltage vectors and the control of flux using voltage vector B, and the figure B the space vector of stator and rotor flux difference frames. The flux, in addition to being present for synchronization, is also used for the calculation of instantaneous powers, where Psi is estimated flux is conserved considering the voltage of the inverter in coordinates alpha beta. The expression of the flux becomes the flowing, and the voltage is obtained from the estimated flux. The instantaneous powers are calculated as flows. Design of a phase PE controller. Figure 1 shows a phase controller architecture. The input membership function error and delta E change error are expressed by a triangle and a trapezoidal curve, and the output membership function Ki is expressed by triangle, as shown in figure 2. They are defined in the interval minus 1 and 1. The control rules are presented as set the rules 7 fuzzy rules of the proposed control for power or DC voltage control. The fuzzy PE control system structure is given in this paper, shows in figure 3. Results and discussion. Simulation results of the PC fuzzy PE virtual flow estimation. So the figure A shows the applied step change of wind profile for the studied system, and figure B presents the waveform of DC link voltage, and figure C shows that our system presents with satisfactory dynamic and an almost zero static error for the axial power. One observes dynamics which reacts quickly and with weak overshoot. The coupling between the two powers is very weak and hardly noticeable. Figure G presents virtual flux angle estimated using fuzzy PE controller. It can be seen that the phase angle waveform of virtual flux is smooth and stable. Then the estimated virtual flux can be used to detect the sector, shows in figure H, used in control of direct power control. Results of DPC fuzzy PE virtual flux estimation and EFOC strategy. Robustness of the command is 9 percentage points, especially for system comprising several interacting entities or systems with strong parameter variation. This figure show THD and power active and reactive of EFOC strategy and the DPC fuzzy PE virtual flow estimation. Comparison to the state of the art. This table summarizes the principal difference between the EFOC strategy and the new intelligent power adjustment, DPC fuzzy PE virtual flow estimation. Conclusion. Using EFOC controller, it's very difficult and complex to design. A high double feed induction generator drive system and the fuzzy PE controller is very complex with respect to the software and requires an extensive calculation that puts extra load and the processor. In this paper, we presented the states variation in an objective of ameliorate the power adjustments, why the DPC fuzzy PE virtual flow estimation, flux estimation can be used for parameter estimation, as well as state estimation is less sensitive to the system parameters variation, and this provides its robustness. A comparison between EFOC and DPC fuzzy PE virtual flow reveals the effectiveness of the first one, and argues that the fuzzy PE virtual flow estimation has a good performance and is the least involved in terms of design and DC link voltage and sector detection with precision and more system stability. Active power. Future work is oriented at experimental validation. Thank you.
Much. And thank you for you.
My name is Shanska. I'm a research professor.
Okay, so I don't know what happened, but anyway, thank you very much for your presentation. Now the floor is open for very few questions, please. Okay, let me have one. Oh, Mohaid, please start it.
Yeah, just I was wondering about basically the novelty of this work, how the author could describe it, and I really would like to understand better about the fuzzy IP. Is it fuzzy integral proportional controller, or I'm understanding it in a different way? Just that, I just would like, as I said, understand about the novelty, why they pursued this kind of a research, and yeah, that's all.
Okay. Ahmed?
Yeah.
What do you think here too? Again, yes?
The fuzzy PE controller, it's two controllers. We have fuzzy and PID controller. And this controller used to ameliorate response time and system stability. And also block diagram is low complexity to other controller.
Yeah, thank you very much. I have also one question, which is that nowadays there is a trend that the towers of these wind machines, wind turbines, can be used to accommodate supercapacitors for energy storage. Would energy storage inside of your system do any benefit from the control and for the easiness of staying stable?
This technique is used just for control power active and reactive, not for energy storage or for.
Okay, so that means that is not help you anyway. Not a help for you anyway. Okay. Yeah. So, gentlemen, ladies and gentlemen, we have finished for today. At 6 o'clock there is the ceremony. Everybody is welcome to join. We will give the best paper awards, and we have just 15 minutes till that to get a glass of water and whatever else. So thank you very much for the participation. We had some technical problems, but anyway, everybody could say his word, and very glad of it. Thank you again, and see you next year.
Thank you very much.
Thank you very much,
everyone.
Okay.
Bye. Bye.
Bye.
Thank you. Goodbye.
Goodbye. Goodbye.
Questionum sipan.
Okay.
Questionum
sipan,
professor.
The 6 o'clock we will still. I invite you to come to the ceremony at 6 o'clock. Usually, at the second day of the conference, there used to be a gala dinner, and during the gala dinner, we were giving these awards. But even now, everybody has to drink a glass of something alone at home. That's very sad. Never mind. Next year. Goodbye.
Goodbye, sir.
Bye.